Prolog provides dedicated predicates for reasoning about integers. These predicates include equality, disequality, less than, greater than, and also a few other predicates. These predicates all reason about integer expressions, which are defined inductively. Variables, integers, and compound expressions are integer expressions. A compound expression is a term such as a plus b, a minus b, a times b, and also a few others, where a and b are again integer expressions. So, for instance, this is an example of an integer expression. This is a compound term with principal functor plus and two arguments, both of which are integer expressions. And with the predicates I mentioned, you can reason about such terms. For example, the predicate hash equals denotes equality of integer expressions, and hash equals of a and b holds if and only if its arguments evaluate to the same integer. And since hash equals is an infix operator, we can write hash equals of a and b equivalently as a hash equals b. These are simply notational variants of exactly the same term. Hash equals of a and b is a term in functional notation, and a hash equals b is the same term in operator notation. So, for example, we can ask, is it the case that 1 plus 2 evaluates to the same integer as 7 minus 4? And yes, this is of course the case. We can also ask, is there some integer r such that r is equal to 1 plus 2? And the system says, yes, r is 3 is the only solution. Or is there some integer y such that 1 plus y is equal to 3? Yes, y is 2 is the only solution. So from these examples we see that hash equals is a true relation and can be used with both arguments instantiated or with variables appearing in either side. In some cases there is of course no solution. For example, if we ask, is there some integer x such that 2 times x is equal to 5, then the system tells us no, there is no such integer x. And when we ask, are there integers x and y such that x plus y is equal to 1 plus 2, then the system tells us this is the case if x plus y is equal to 3. So we call this a conditional solution. It tells us that yes, this holds if something else holds, and the condition we get is in this case a simplified version of the original query. And as in all cases above, the answer is declaratively equivalent to the original query. Note the difference between hash equals and plain equals. Hash equals denotes equality of integer expressions, and in this sense 1 plus 2 is equal to 3. On the other hand, plain equals denotes syntactic equality, and for this reason 1 plus 2 is of course not equal to 3, because syntactically the term plus of 1 and 2 is different from the integer 3. We say that hash equals denotes equality modulo integer arithmetic. And this can be regarded as a generalization of syntactic equality provided by plain equals. And the hash sign is consistently used also for several other predicates that reason about integer expressions. For example, is it the case that 0 is not equal to 1? Yes, this is of course the case. Or more generally, is there some integer x such that x is not equal to 1? And as answer, we get the set of all integers that satisfy this constraint. And 0 is of course included in this set as one particular solution that satisfies this constraint. These predicates are available right from the start in GNU Prolog, bprolog, and several other systems. However, in some Prolog systems we need to import a dedicated library to use declarative integer arithmetic. For example, in Sixus Prolog we can use the directive useModule library clbfd. And I recommend that you configure your system to load this library automatically every time you start the system, because almost all Prolog programs also need to reason about integers, and therefore it makes sense to make these predicates available by default. Using these predicates as building blocks, we can express more complex relations over integers. And as one example, let us consider the factorial relation. The factorial of a non-negative integer n is defined as the product of all integers from 1 to n. By convention, the empty product is 1, and therefore the factorial of 0 is 1. So let's define the relation n factorial of n and f, relating an integer n to its factorial f. We can write down one special case immediately. The factorial of 0 is 1, so we can write this down as one simple Prolog fact. So what remains to be described is the case where n is greater than 0. And we must express what constitutes the factorial in this case. So let's suppose we already know the factorial f1 of n1 if n1 is n minus 1. Then a bit of reflection tells us that in this case the factorial f of n is n times f1. So this completes the definition. So let's consider a few sample queries. For example, let's start with the most general query where all arguments are fresh variables. When we ask which solutions are there at all, then we get the factorial of 0, of 1, of 2, of 3, of 4, and so on. So we can use this predicate to generate solutions. And we can also ask more specific queries. For example, we can ask, what is the factorial of 42? And we get one solution. And on backtracking, the system tells us that there are no other solutions. So this false here simply means that there are no other solutions. And we can use the same predicate also in the other direction. For example, we can ask, is there some integer n such that the factorial of n is 120? And this also works. From this we see that n is 5 is a solution and is the only solution. And one major advantage of this declarative integer arithmetic is that you can also freely exchange these goals and study the operational effects of changes. For example, we can exchange these two goals or these two goals. And these different implementational variants of the predicate also have different termination and performance characteristics. For example, they may be more efficient in a particular case, or they may terminate better in one particular case. So using this declarative integer arithmetic, you can try these variants and study the effect of such changes. And predicates over integers are also often used for solving combinatorial tasks, because each finite combinatorial task can be mapped to a problem over integers. Declarative integer arithmetic is also called CLPFD, which stands for Constrained Logic Programming over Finite Domains. And CLPFD constraints are frequently used for solving combinatorial tasks. For example, a chicken farmer also has some cows for a total of 30 animals, and the animals have 74 legs in total. How many chickens does the farmer have? So this is a task that you can already solve with the predicates we have seen so far. And for this task we assume that a cow has 4 legs and a chicken has 2 legs. Here is a link with more information about CLPFD and also links to further such tasks.